Kia ora and welcome to Lecture 8 for 161324 Data Mining. So today we're continuing a classification and we're going to be looking at a very common classifier, which is a logistic regression. So recall that LDA, KDA and naive Bayes classifiers are all generative in that they model the probability of a class given the predictors by first learning the opposite probability, the conditional probability with it the other way around, that is the distribution of the predictors within each class, so the probability of observing a particular combination of predictors within each class, which is Px given j, or in the notation from last week, f sub j. And of course the prior probability of the class before we've looked at the data, which might be the proportion of data that we expect to observe of each class. And then they use Bayes' theorem to combine fj and πj in order to derive or to generate what the posterior probability of the class given the predictors are, which is the thing we're really interested in for classification. The alternate to that is to attempt to learn the posterior probabilities, the probability of each class given the predictors directly. And this is what gives us discriminatory classifiers, which is a bit of an odd name because, of course, we looked at LDA, which is linear discriminant analysis, and KDA, kernel discriminant analysis, because those are actually generative, not discriminatory. So there's a little bit of wordplay there. So one approach to creating a discriminative classifier is to assume that the probability that we're interested in takes a particular parametric form, i.e. that we've got an equation directly that relates the x's to that probability that we're interested in. And logistic regression does this. So it's logistic regression is part of a broad class of methods known as generalized linear models. So they take the linear model and they generalize it by essentially having a link function between the linear predictor and the outcome. So the outcome does not need to be normally distributed. It may be distributed using some completely separate distribution, and then there's a link function that ties the mean and the variance of that distribution to the linear predictor. So logistic regression models a binary response, so it's only two classes with the values written as 0 and 1. Okay, so they code for the first and second class respectively. So y equals 1 is the second class and y equals 0 is the first class. And the model is then described in terms of the probability of the second class, so the probability that y equals 1. The idea being you've only got two, so if you know the probability of the second class, then you can derive the probability of the first class just by subtracting that probability from 1, right? Because the two probabilities have to add up to 1. Now this idea can be extended to more than two classes, and we'll see that towards the end of the lecture when we get multinomial regression. So we want to estimate the posterior probability that y equals 1, so that's the probability that y equals 1 given a combination of predictors x, which is the same as the probability of the second class. Now, of course, that probability is a number, so why not just use linear regression, right? So we could just have that probability is just equal to some linear predictor that we've got written here. Okay, note that there's potentially some confusion, so often we use lowercase p for the number of predictors, and we also use p for a probability because probability starts with p, so just note that these are different p's if you like. Perhaps you might want to use a different symbol for the number of predictors. The problem with doing this using linear regression is that our p here, our outcome, is a probability, so it's constrained between 0 and 1. Right? We can't have a negative number, we can't have something more than 1 because probabilities only live between 0 and 1. But the linear regression, the linear predictor, of course, does not respect that. So for example, if we did fit a linear regression we had just a single variable x, and perhaps we got this formula here, right? So that our fitted model is p equals 0.3 plus 0.1x. Then if x is more than 7, right, and we plug, so say x is 8 and we plug it in here, we'd get 0.3 plus 0.1 times 8, which is 1.1. So we're saying the probability of the second class is 1.1, which is more than 1. That's a problem. Similarly, if x is smaller than minus 3, then say it's -4, we'd have 0.3 plus 0.1 times -4, which is 0.3 minus 0.4, which is minus 0.1. And you can't have a probability that's negative, so that doesn't make sense either. Okay, so while we could model this using linear regression, it probably doesn't make all that much sense. So one solution is to use the sigmoid function that we saw for neural networks, right? So you remember the sigmoid function mapped the real line, so between minus infinity and plus infinity, into the interval 0 to 1, which is exactly what we want to do. We have a linear predictor that can take any value at all, and we want to then constrain that linear predictor to being between 0 and 1. So putting it through a sigmoid function is one way to do that. And you remember that the logistic function, or the sigmoid, takes this formula here. So we're going to say that our outcome that we're interested in, P of x, is going to be 1 over 1 plus e to the minus theta. And then theta is going to be our linear predictor. So it's just like the activation we used in a neural network. And then we can inverse this function just by rearranging it for theta, right? So you'd go 1 over P of x would be 1 plus e to the minus theta x. So 1 over P of x minus 1 is e to the minus theta x. You take logs, negate, and so on and so forth. And we get this formula here, relating theta back to P. All right, so this formula here is called the logit, or the log odds function. And so our formulation for linear regression, for logistic regression, is that our outcome is modeled using P of x as the probability of y equals 1, and then the logit of that P of x is then a linear predictor. Okay, so recall what the shape of these curves are. Here's the logistic function here, so it takes any value for theta, which is going to be our linear predictor, and can potentially give us any number at all. And it's going to then map that between 0 and 1. And it has the nice property that when theta is 0 is when P goes through 0.5. Right, so if theta is positive, then, so that's the linear predictor is positive, then we're more likely to be the second class, right? Because we're modeling so P here is the probability of the second class, or P y equals 1. So if the linear predictor is positive, we're more likely to be y equals 1, and if the linear predictor is negative, we're more likely to be y equals 0. So just by looking at the linear predictor, and we don't have to do any transformation or anything, we can figure out what the likely class is. So here's what the inverse of that function looks like. It kind of looks like a reflection in y equals x, right? So you can see that that for probabilities close to 0, the linear predictor is highly negative, and for probabilities close to 1, the linear predictor is highly positive. And it's only really in sort of plus or minus about 4 that you actually get values between 0 and 1. Otherwise, they're very, very close to 0 or very, very close to 1. So the formulation is this here, right? So we've got a probability of the second class, and all we do is we model our y's, which are 0 or 1, like you're tossing a biased coin. So it's a Bernoulli distribution or a binomial distribution with just one trial. Okay, and so that's our formulation for y, and then we model P by on the logit scale. So we take the logit of P and model that with a linear predictor. Okay, and this is the general formulation for all generalized linear models. So we just may have a different link function. So for example, with Poisson regression, y is a Poisson variable with some mean vector lambda, which is the expected number of counts. So Poisson distribution is useful for modeling count data. And then we'd model the link function we use as the log instead of the logit, right? Because we're not concerned with keeping the expected count between 0 and 1. We do want the expected count to be bigger than 0 rather. So we use the log rather than the logit. Okay, so that's the formulation for logistic regression. So we have a target which is basically 0 or 1, or just two classes. And then we've got xi is our vector of predictors or features for that observation. And because it's a linear model, this bit of it anyway, our predictors can be numeric or categorical because we can encode them using indicator variables, just like for linear regression models. So these betas are unknown regression parameters, and they will be estimated from the training data. Now, the estimation is done in a slightly different way than linear regression. So you recall for linear regression, we found the optimal beta coefficients by minimizing the sum of squares. And the reason that worked for linear regression was that the outcome was actually a normal distribution, right? So for linear regression, we assume that y is normal, conditional on the linear predictor, i.e. the residuals are normal, right? That's the assumption that we make. And the normal distribution, if you look at the probability distribution of that, then that is maximized when the sum of squares is maximized. And we do a similar thing here. We maximize the probability of observing the data, which is called the likelihood, in the same way, but it doesn't collapse down to the nice sum of squares expression that linear regression does. Instead, it is this expression down here. Okay, so this is what the likelihood looks like. So this is just the Bernoulli distribution here. Okay, and we've got independence, so we can just product over the independent observations. Okay. In practice, we maximize the log likelihood. Okay, so this is a typical thing that's done. So instead of trying to maximize this thing with a product in it, which is quite difficult, we end up maximizing a thing with a sum, which is a bit easier to do in a computer. Okay, and we extract what's called the maximum likelihood estimate, which is just the values of beta that make this as big as possible. So that's the idea is we want to find which values of beta give us the highest probability of observing our data. Okay, and that would be the optimal beta for that solution. So there's more on GLMs in 161331 that's actually incorrect. I'm going to fix that today. So if you're interested in more generalized linear models, then you can do biostatistics, which is 161331. Okay, so how do we do this in R? Well, generalized linear models are fit using a syntax very similar to linear models. It's just GLM rather than LM. And the extra parameter it has is the family. Okay, so the family in the case of logistic regression will be binomial. Okay, otherwise it takes a formula and a data frame in the same way. The only thing you've got to watch is that the outcome variable has to be a binary 0-1 variable or a 2-level factor. Okay, so if it's a 2-level factor, it would automatically convert it to binary for you and take care of all that stuff. So let's have a look at an example from the Swiss banknotes. Right, so here we have, we're just using the margin. Right, so type, so that's the outcome class, whether it's forged or genuine. In terms of margin, family is binomial from the Swiss data, we fit that, and then we'll have a look at the summary output. And you can see that the summary output looks somewhat similar to the summary output for a linear model. Right, you get this table of coefficients. Okay, so that's your betas. So this is beta 0, which is your intercept, and beta 1, which is your margin. You get p-values and so on and so forth as per usual. You then get some information about the fit down here, just like you did before. In the linear model, it's just different, right? Because we're not minimizing sum of squares anymore, so we don't have residual variance. Instead, we have this thing called residual deviance, which is kind of an analog to the sum of squares. So what we notice is that the coefficient of margin is negative. So that means that as the margin increases, the probability of the note being genuine decreases. Okay, so the probability, the outcome is always the second class. Okay, so the first class is forged, second class is genuine. Okay, so we're looking at the probability of it being genuine. Okay, so because the margin, the coefficient of margin is negative, then as margin increases, that probability is going down, right? And in fact, it goes down according to this. So this is our sigmoid that we fitted to the data, right? So there's kind of a it's the opposite of the usual one. The usual one starts here and goes up like this, and that's because the coefficient of margin is negative, right? So we've just flipped it round, and so you can see there's kind of a threshold here that where the probability of being a genuine note surpasses the probability of it being a forged note, right? So if the probability of the genuine note is more than half, then the probability of it being forged must be less than half, right? Because the two things add to 1. And so there's some threshold here at about 9 1/4 that if the margin is bigger than 9 1/4, then the probability of the note being genuine falls below a half, therefore we're more likely to be forged. If the margin's less than 9 1/4, it's more likely to be genuine, which is a similar result to what we got last week with LDA. Now, just like with linear models, we may not want to use all of our predictors. Okay, so there's a bias variance trade-off in the same way as there was for linear regression, in that by including predictors that perhaps may not make a difference to the outcome, you have to estimate the parameters thereof, right? They're nuisance parameters, and so you may be not really benefiting from the model fit, so your bias won't really change, but you're having to estimate them, so your variance goes up. Okay, so there's that variance bias trade-off, exactly the same. So one way we can do it is we could use stepwise regression, just like we did for logistic regression. Okay, so you just fit a GLM. So here we're fitting a one with all variables. Okay, and then we're running a step on it. Okay, so you can see that when we do that, it uses the AIC criterion, and so the model with both variables in it has an AIC of 13.2, and if we remove the margin, our AIC gets worse, i.e. it gets higher, and if we remove the diagonal, then it gets even worse again, right? So the best model in this case is the full model, so we should use margin and diagonal. So given a logistic regression model, how do we do classification? Well, we've sort of hinted it back on this figure here, right? We use the linear predictor to work out what that threshold is, and once we've worked out where the threshold is, we just evaluate. We basically just put our new observations into the linear predictor, and then based on whether that linear predictor is positive or negative, we can decide which note type it is, so whether it's genuine or forged. So let's see how that works. So logistic regression is estimating the probability of a 1, okay, or a probability of the second class. So we can choose a threshold to assign a new observation in a test set to one of those classes, and the typical threshold to use is just 0.5, right? Because if the probability of the second class is more than 0.5, then it's more likely than the first class. If the probability of the second class is less than 0.5, then it's less likely than the first class. So 0.5 is a natural threshold to use. So we're going to assign to the second class if and only if the probability of that second class is more than a half. And then we can just use some maths to figure out what the consequence of that is. So recall that our probability is that logistic equation, or the theta is the logit of p. And so if the probability here is more than a half, then this thing here must be more than a half, right? And if this thing here is more than a half, then the only way that can be more than a half is if the denominator here is less than 2. Right, because we go 1 over something smaller than 2 is bigger than 1 over 2, right? And the only way that this can be less than 2 is if this exponential bit is less than 1, right? So thus we get this equation here. And then we can just take the logs and do the negation. So the only way that an exponential of a negative number is less than 1 is if that number is positive. Okay? So we're going to assign to class 1, which is the second class, so y equals 1, which is the second class, if and only if the linear predictor is positive. So we don't have to bother with all the logistic formula, we just have to look at the linear predictor directly. right? Which is a nice easy computation, isn't it? If you know your x's, you just bung it into your linear predictor, you get a number. If that number's positive, then it's more likely the second class. If that number's negative, it's more likely the first class. Okay, so if we have a look at our summary of that first model that we fit, we could actually write down what the linear predictor is. So the linear predictor is going to be 19.97 minus 2.16 times the margin. There it is there. And so we can see that there's going to be a threshold here, right? If margin starts being bigger than about 9, so if margin's 10, then this would be 19.9 minus 21, which is a negative number, right? And so we'd assign it to the first class. But if margin's smaller than 10, say margin's only 9, then this would be 19.96 minus about 18.2, which is a positive number, so it's going to be genuine. So there's some threshold between 9 and 10 that switches between forged and genuine notes. Okay, and we can work that out directly, right? We can just rearrange that equation. So rearrange that equation. You put the 19.9 over there and then divide by the 2.15, and you can find that value 9.25, which is what we got we saw on that plot earlier on. And when we plot the data, the training data, we can see that that's actually a very sensible place to cut the two groups, right? So this is a B-swarm plot, right? It's just a dot plot where the y-axis is the margin here, and the x-axis is just centered around forged, but the actual value here is not important. So it's just jittered in the x direction here, just so that we can find all the points. And I've just coloured them based on the group, and then used alpha to show the ones that are incorrect. So you can see here that 9.25 is a sensible place to split the training data. The same idea works if you've got multiple variables, right? So the classification rule for the second model that we fit, which had both margin and diagonal in it, would be minus 985.26 minus 4.9 times the margin plus 7.3 times the diagonal. Okay, and we would assign an observation as y equals 1, which would be genuine, if when we bung the margin and diagonal into that equation, we get a positive number. And so that's forming a straight line on the margin versus diagonal plot, okay, and there it is there. And if we're on the right of this line, we're forged, and if you're on the left of the line, you're genuine. And that's because if you're above the line, you're genuine, and if you're below the line, you're forged, right? That's just the formula of the line. If you're positive, you're on this side of it. If you're negative, you're on this side of it. Okay, so you can see that this is doing extremely well, right? There's only one wrong here, this observation here. So it's doing similar to LDA. It's also providing a linear discriminant. So it's a hyperplane that's separating the two groups, but it's a different hyperplane than LDA. Okay, because it has different underlying assumptions. LDA, remember, had the assumption that these two things were bivariate normal with the same covariance and just different centers. LDA, logistic regression, instead is modeling the relationship between the logit of the probability and the margin and diagonal using a linear regression. So we classify y equals 1 if and only if the probabilities are bigger than a half, which translates down to the linear predictor being bigger than 0. Now we can use predict or augment from the Broom package to estimate the posterior probabilities as well. But one thing you've got to note is that prediction for linear regression, in fact for any generalized linear model, is on two scales. So predictions can either be on the response scale, which is the y scale, so that's be a probability between 0 and 1, or they can be on the scale of the linear predictor. So that's before the we've unlogited or logistic the linear predictor. And by default, it's going to give you a prediction on the linear predictor scale. Okay, so we're going to have to use it as if it's a prediction on the linear scale. You can change it, so you can with augment, for example, or predict. You can specify that the type of prediction is going to be the response rather than the linear predictor. So for example, if we use the Broom package and we use augment, and we just take a look at the output, then what you'll see is the dot fitted parameter that Broom has added, that the augment function has added. That's the linear predictor. So the value of the linear predictor for the first observation in the test set is minus 18.8. Right, so it's a negative number, so that one's going to be forged. Predicted forged. It's actually forged as well. The second observation, it's a positive number, so that's going to be predicted to be genuine. And the third observation is going to be predicted to be forged because it's a negative number. If instead we actually want the probabilities directly, then we can just put type.predicted is equal to response, and then we get probabilities directly. So this is the probability of it being genuine is essentially 0 because it's forged. The probability of it being genuine is essentially 1, and we're getting that correct. Probability of it being forged is essentially, probability of it being genuine is essentially 0, so our interpretation would be that it's forged. Okay, and you can see that from here as well, right? So the fitted value here is exactly minus 18.77, and if you bung that into the logistic equation, we get 1 over 1 plus e to the 18. Now e to the 18 is a very big number indeed. So this is 1 over a very large number, so it's essentially 0. In fact, it's this number here. Right? So that's the relationship between those two things. So we can do prediction basically just by doing predict, getting our fitted, and then deciding whether it's positive or not. So this is one way to do it, right? So we're doing our augment to get our fitted value, right, that column there. And then we're going to work out whether we have a predicted class based on whether this is negative or not, right? So we're creating a new factor based on whether it's fitted, whether the fitted value is greater than 0. And if it's true, it's going to be genuine. If it's false, it's going to be forged. Okay, so these are our predictions there. And you can see that we're getting the predictions right for the most part, but some of them we get wrong, such as this one here. Observation 10, we can see that we're predicting that it's forged, but it's actually genuine. Now, the problem with doing this, of course, is you've got to be really careful that you get these levels around the right way. Right? I'm saying that fitted greater than 0 being true is genuine, and fitted greater than 0 being false is forged. I've got to make sure that I've encoded my factor the right way around. So a much easier method, of course, is to just use the tidy models framework. So in the tidy models framework, that takes care of all the factor stuff for us. Make sure everything's in the right order. We don't have to worry, right? So I highly recommend just running it in this way here. Right, so logistic regression, logistic reg is the model type, and then everything else is the same as what we've seen before. Okay, so there's our prediction. It gives us our predicted class. It gives us our probability of prediction of it being forged and genuine, just like we did for LDA and KDA. Okay, and of course we can then run confmat and yardstick in order to get our confusion matrix, and you can see that we're doing extremely well because this is a nice easy data set to classify. So let's now look at a more interesting example, one that has many more variables and perhaps is topical, though less topical as time goes on, as people kind of forget that COVID-19 is still a thing. Of course it is. You should still be very careful, and if you are sick with typical symptoms of COVID-19, which are getting more and more general as time goes on, you should test and avoid going to class and work and so on and so forth, and being around people, particularly people that may have worse immune systems, such as older people and the like. Okay, so this is data from New Zealand. It's published data, so we've got a bunch of data on confirmed cases and those that were tested but were tested negative using PCR. So this is from the early days of the pandemic, along with a wide variety of reported symptoms, their age and sex and so on. And so there's a link to the paper if you wish to read it for yourself. You're welcome to. One of the great things about being at a university is that you often have, if you're on the Massey network, then you will have access to that paper, along with many millions of other papers. And they use decision trees and random forest, among other things, to identify symptoms that are more likely in confirmed cases than those not a case. So we've got the data here, and we're going to process it a little just by converting everything to factors and then changing the status variable so that not a case is the baseline and case is then the probability that we're interested in. And we're going to start by splitting the data into training and testing sets, just in the usual way. And our goal then is to predict the status of an individual given their symptoms. So given a set of symptoms, is this person likely to be a case, or is this person likely to be not a case? So if we look to see the association between being a case and being confirmed, what we could do is we could have a look at the characteristics of the different symptom variables by whether they're a case or not a case. So what proportion of cases, confirmed cases, had a particular symptom, and what proportion of those that were confirmed to be not a case had the same symptom. Okay, so we can do this just by counting, right? So we group by the status and the different variables. So I've pivoted longer here to make things untidy. Got rid of the age group and the month and the sex first, and then so that we're just looking at the symptoms. Pivoted longer to get it untidy, so we're name, value, key pair form, and then we can group by the status, the name, and the value in order to basically count across all possibilities. So count across all symptoms, did they have it or not, and were they a case or not. And then we work out the proportion, which is just going to be n over the total in that group, and we're going to just look at the yeses, i.e. the proportion at which they said yes, they had a sore throat, for example, and then we're plotting them. So you can see here that there's a difference in the pattern, right? So that those that were confirmed tended to say yes to multiple symptoms. Okay, yes, they had a cough, yes, they had a fever, yes, they had a headache, yes, they had a sore throat and weakness, and so on. Okay, but were less, and whereas those that were not a case tended to have a cough and a sore throat and perhaps a fever, but had less, but fewer of them had some of the other symptoms. In particular, these last two, anosmia and ageusia. I don't know if I'm saying those correctly, but anosmia is basically the lack of sense of smell, and ageusia is the lack of sense of taste. So you can see that at least in the early part of the pandemic, so this is the original strain of COVID-19. It's not Omicron. It's not the funky ones that we have now that have rather different symptoms. In particular, the newer ones tend to have gastro symptoms, whereas and less of the lack of taste and lack of smell like the original one had. So you can see that there's a clear difference here, right? So this is a symptom that's telling you a lot about whether things are cases or not. Okay, and we could fit a logistic regression to this data just by fitting everything, right? And we get this big output in the summary table, and just going going down it and looking at the things that are important. We've got a very low p-value for anosmia, which is the lack of smell. And so if you said yes to that, you're much more likely to be a case. There's some protective factors. So let's have a look down here. If you've got a sore throat, then you're actually less likely to be a case, simply because more non-cases said they had a sore throat. If you're a male, you're more likely to be a case. Right, that's a positive number there, so you're more likely to be a case. I'm just trying to find things that are significant. So the lack of taste is significant. Joint pain is significant. Weakness is highly significant. So those are the things that are associated with cases. So how well do we do? Well, we can do our prediction, and we find that that we're doing really well at predicting those that don't have COVID. Right, so they're not a case. We're getting 1,130 out of the total 1,164 correct. But we're doing really badly at predicting the actual confirmed cases. In fact, we're getting about 2/3 of them wrong. Right, so out of the 281 cases, confirmed cases of COVID, using our logistic regression model that we fitted to all the predictors, we're actually only getting 97 of them right. So 184, we're saying, given your symptoms, you don't have COVID. Now, that's probably not a sensible thing to be doing in a pandemic situation, right? If we rolled this model out to general practitioners in New Zealand, and we were, at the beginning of the pandemic, when New Zealand, of course, basically kept COVID out for almost 2 years. When someone rocks up at the GP and we tested them and said, actually, given your symptoms, you're not likely to be a case. If they were, of course, a case, then that's a very bad thing indeed. So in practice, we don't want to be using just the overall accuracy, which of course is pretty good here. We're getting 1,200 out of about 1,400 correct. So we're doing pretty well, but that's only because we're doing really, really well on the not a case. It's because the data are imbalanced, right? There's not the same number of cases and controls, cases and non-cases. And so a really dumb model that just says everyone is not a case will do almost as well as this model here. Okay, but that, just saying, I don't care what your symptoms are, I'm just going to say you don't have COVID, that's not a good baseline in this situation. So how can we fix this? So one way we can do it is altering the classification threshold. So by default, we're going to the logistic regression classifier uses the probability of the second class being more than 0.5 as sort of the default threshold, which is assuming that each class is equally important, right? If it's more than 0.5 for the second class, then it has to be less than 0.5 for the first class, right? So there's a symmetry there. But in a pandemic situation, it's much more important to tell a case that has COVID-19 that they are a case than it is to tell someone that's not a case that they're not a case, right? Worst case is that if you tell someone that that doesn't have COVID that they do have COVID, then the worst case is they're going to be isolated, right? So they're going to isolate for a couple of weeks from their family members and so on, just to make sure that they don't infect anyone, right? But there's going to be no real disadvantage other than inconvenience to that individual. On the other hand, if we tell someone that does actually have COVID that they don't, so we make a mistake there, then what's going to happen is they don't isolate, of course. They're going to go out in the community, they're going to go to work, they're going to go to school, education settings and so on, and they're going to infect other people, right? So the consequence of getting it wrong for cases is much, much worse than the consequences of getting it wrong for non-cases. And that's the case with many sort of medical diagnoses, right? So for example, if you go and have a screening test for a cancer, then if we get that screening test wrong and say, oh, I'm sorry, you do actually, we think your markers for prostate cancer or whatever, your PSA test or whatever it might be, or for breast cancer, are high, and so you may have prostate cancer or breast cancer. The consequences of that are that you then go for further treatment and perhaps have a biopsy or something like that, which is extremely inconvenient for the person, or maybe inconvenient, there may be side effects and so on, but that consequence is less bad than telling a person that actually has cancer that, hey, you don't have cancer, right? Because the consequences of that is that then they're not followed up, that cancer then gets worse and perhaps becomes untreatable. Okay, so the inconvenience from saying, hey, maybe you do have something here, we need to follow it up, is less than the consequence of getting it wrong in the other way. So sometimes the 50-50 doesn't make sense. So in this pandemic situation, it doesn't make sense, right? So we'd want to use a lower threshold than 0.5 in order to classify more people as having COVID compared to saying people don't have COVID, right? So we want a lower level of threshold there. And what we're doing by moving the threshold is trading off sensitivity and specificity. So the sensitivity of a logistic regression or a diagnostic test is the probability of predicting a true case given that they are a true case. So this is the probability of saying to someone that does actually have cancer, hey, you've got cancer. Specificity is the probability is the opposite. So it's the probability of saying, hey, you don't have cancer when they really don't have cancer. And tests are never perfect, so these probabilities are unfortunately never 1, right? And the threshold in logistic regression is trading off these two things. So by lowering the threshold, you predict more cases, and if you're predicting more cases, you're basically increasing the specificity because you're increasing the number of cases you predict, which must mean that you're increasing the number of cases that you predict that are actually true cases. Increasing the threshold is then increasing your specificity. So increasing the threshold would be predicting more non-cases, and so you'll be predicting out of the true non-cases, you'll be predicting more of them, so you'll be getting higher specificity and lower sensitivity. So you're always trading these two things off by altering that threshold. And there's this thing called the receiver operating characteristic, which describes how the sensitivity and specificity change as the threshold changes. Okay, and it's usually plotted using sensitivity against 1 minus specificity, and there's the ROC curve in the yardstick package to do so. And you get a curve that looks like this, right? So this is from our COVID data. We just get our predictions and we pipe it straight into RUC curve, and we have to tell it which level is the true positive, right? Which is the second category, the probability of being a confirmed case. And then we just plot a 1 minus specificity versus sensitivity. So here it is here. Okay, and there's our 0.5 threshold. So you can see that when we use the 0.5 threshold, we have very low, we have very high specificity, which means low 1 minus specificity. So we're getting the non-cases right almost always, but we're getting the true cases wrong almost always, right? So the sensitivity here is only about a third, 33%, which is what we saw was the classification rate for non-cases. So sensitivity is just probability of getting the COVID cases correct, which was just that column here. So all we've done is converted this table to percentages, right? So if you convert this to a proportion down the column-wise proportion, you're going to get close to like 0.95 or something here, right? And you're going to get close to 0.35 here. So 0.35 here and 1 minus 0.95 here. Okay, but you can see that as I move along the curve, I trade these things off. So as I move towards, as I lower the threshold, I'm going to be increasing my specificity. My specificity is going to go through 1. So that means that as I lower the threshold, I'm going to start getting all the non-cases correct. But I'm going to start also getting all the cases wrong. That's a bad thing. As I increase my threshold, I'm going to start getting all the cases correct. Right? My sensitivity is going to go up to 1. But I get all the non-cases wrong. Right? So up here, what I'm doing is I'm basically saying everyone's a case. All right? So I'm going to get all the cases correct, but I'm going to get all the non-cases wrong. So that's bad in some senses. Down here, I'm going to get all the non-cases correct, but I'm going to get all the cases wrong, and that's probably worse. So we probably want to be further up this way than we want to be down this way. So we want to increase our threshold. And one way to do that is to just find the point that's closest to this top corner here. So find the point that maximizes the sum of the sensitivity and specificity. And this gives us a new value of our threshold, 0.185. So if the probability from our linear predictor is, from the logit of the linear predictor is 0.185, more than 0.185 we'd assign it to be a case. Okay, and when we do that, we get a better picture in terms of our cases. Okay, so we're going to do our prediction based on whether the probability of the confirmed case is more than 0.185, which is the threshold that we defined down here, instead of 0.5, and then we can see that we get more of the confirmed cases correct. As a consequence, we get more of the non-cases wrong. But of course, in a pandemic situation, this is the number we want to get right. Right? We want this number to be as big as we can without inconveniencing too many people. So there's a trade-off, right? We don't want to just take the threshold all the way to 0, so that we're saying if you've got any of these symptoms, you should be treated as a case. We don't necessarily want to go that far, but so there's still a trade-off there, but we still want to increase this number as much as we want. Now, with further testing that was available after this situation, so at this point we only had PCR testing, right? So I guess with PCR testing, if you said everyone was a case, you'd have to have a follow-up PCR. Now we've got rats, of course, right, which are extremely, they aren't particularly uncomfortable to do at all. You can do it at home. You can get them for free, or at least I think you can still get them for free. Who knows whether they'll be free for much longer. But it's something that you can quickly and rapidly test sort of on a daily basis. So at this stage, saying actually if you've got any of these symptoms, you should stay home and test. That would make sure that you get all cases and all non-cases, and worst cases you're just having non-cases stay at home and test, which isn't a huge consequence. Obviously there's some consequence there, there's economic activity and all that carry on, but still in terms of public health there's very little consequence there. So there's always a trade-off, and the size of the trade-off is going to depend on the situation. Okay, the other way to do that same idea is, instead of moving the threshold, we could instead assign a weight or a cost to getting things right or wrong. Okay, so in this example here, with the COVID, what we want to do is we want to prioritize getting confirmed cases wrong. And we don't really care as much if we get non-cases wrong. So one way to do that is to say, well, if we get a case wrong, we're going to assign it a cost of, say, $10. And if we get a not a case wrong, we're going to assign it a cost of $1. Now, those numbers are completely arbitrary. The only thing that matters is the ratio between them, right? So all we're saying is that if we're getting the cases wrong, then it's 10 times more costly. The consequence is tenfold more bad, if you like, than getting not a case wrong. And so we set up the simple cost function. If we're truly not a case, but our prediction is that we are, then that has a cost of 1. And if we truly are a case and our prediction is that we're not, that has a cost of 10. The other cases, which are getting them right, they have a cost of 0, of course, right? And then we're going to look at the cost function with our normal predicted class, and then we're going to look at our cost function with our alternate predicted class, which is the one that we did back here, right, based on our other threshold. And you can see that when we do that, the cost with the 0.5 threshold is 1,874, and the cost with the alternate threshold is only 1,058. So we've decreased the cost by over a third by moving the threshold. Okay, so this is an alternate way, is that you can say, if you can quantify the downside for getting it wrong in each case, then you can use that quantification to adjust the threshold directly. Okay. Right. So what about the case where we have more than 2 classes? Well, the idea of logistic regression can be extended just by basically partitioning the data. So all we do is we basically say, okay, so say we've got 3 classes, then what we do is we model the probability of the first class with a logistic regression versus the other 2, right? So we say, what's the probability of being in the first class compared to either the second or third class? And then conditional on it not being the first class, we then model the probability of the second class conditional on it not being a third class. Right, so there's 2 layers of logistic regression to determine the first 2 classes. The third class is then determined directly. Just like in logistic regression, we model the probability of the first class, the second class was the probability of the second class, the first class is then determined directly, we do the same thing, right? So we model the probability of it being the last class, the probability of it being the second to last class, probability of being the third to last class, and then the first class is the default. Right? So so that's the same idea. So this is referred to multinomial regression, referred as multinomial regression because there's multiple classes for the response. So in this case, there's basically, if you have C classes, then there's C minus 1 linear predictors, each of which have P plus 1 parameters. So in total, there's C minus 1 times P plus 1 parameters, right? So if you have 3 classes and 10 predictors, then you're going to have 22 parameters. So quite a lot to estimate. And it turns out that multinomial regression is actually equivalent to a classification neural network that doesn't have any hidden layers but has a sigmoid transformation on the output. Right? So you remember a neural network, if you had hidden nodes, you did a linear combination of the predictors and then you did a sigmoid. And then your outcome node was just a linear prediction of your hidden nodes. Well, you can do the same thing here, except you just get rid of that hidden layer and you do your sigmoid function on the output. So the multinom function, i.e. the function for fitting multinomial regression, is actually done by the neural net package. Now in practice, of course, we'll use tidy models for that, and so we'll use the multinom reg specification, and we're going to use, we've just got to be clear that because it's been fit with a neural network software, so it's been fit by back propagation, then the scale of the predictors is important, right, for numerical consequences, because we're doing that exponentiation. So we've got to scale our predictors that are large in magnitude down first, using a recipe, for example. So as an example, we're going to look at some computerized wine tasting. So we have some data on Italian wines. We have 100 records in the training set, 78 records in the artificial test set, and the aim is to classify the cultivar, it's a type of grape, based on 13 chemical measures. And the cultivar has 3 classes A, B, and C. So we're going to read our data in and convert the outcome variable cultivar to be a factor. Right, so we can see that we have our cultivar, A, B, or C, and then we have a number of numeric measures. We've got some more variables: color, hue, OD ratio, and proline. So we're going to fit using the parsnip setup. So we go multinom reg, we fit our model, and then do the usual combination of parameters. And so we can see here that these are all our coefficients from the model. So we have an intercept for the B and the C classes. We don't have the A class listed because that's the baseline class, right? So the B here, so the C here is estimating the probability of class C. The B here is estimating the probability of class B, and then A is then determined because it's not B and not C. And here's our confusion matrix, and you can see that we're doing really, really well. We're only getting 4 wrong. Now, just like with logistic regression, we may want to also do stepwise regression, and we can do that in the same way. The only trouble is that you have to do it outside of the tidy models framework because it doesn't work within the tidy models framework. So you'll have to fit it back with multinom and then run your step, and then it will go and reduce the model down. So you can see here that it's reduced it just down to 4 parameters: alcohol, flav, hue, and proline. Now that we know those 4 parameters, we could actually refit the model in the tidy models framework, right? So here's our model fit in terms of those 4 parameters, and that then allows us to use augment and confusion matrix and so on in order to do our prediction. And you can see that it's slightly different, right? In this this model, we're getting all of A and all of B correct, and we're just getting some of all of C correct, and we're just getting some of B wrong. Whereas back in the original model with all the variables, we got one of the C classes wrong, all of the A correct as well. So we're doing just as well. Our misclassification rate is the same, but we're using less data. Okay. So in workshop 8, we'll have a play with logistic regression and multinomial regression.